In this video, we're going to discuss solving quadratic inequalities. Now, there are two types of quadratic inequalities. There are two variable quadratic inequalities and one variable quadratic inequalities. So the first thing we're going to go over is the two variable quadratic inequality. And this is going to be pretty familiar because you do two variable inequalities in all different types of functions. You've done two variable linear at this point inequality and two variable absolute value inequality. So here's an example. Okay, we're going to solve for negative y plus 2 is less than, let's do x squared plus 4x minus 1. Okay, so the solution, we can see it's a two variable because we have x and y. It's a quadratic, okay? And our solution to a two variable quadratic inequality is going to be all of the ordered pairs, okay, x comma y, that make this statement true. Okay, that is your solution. So the only way to show your solution, if it's in an infinite set of ordered pairs, okay, is to graph it. Okay, so we have to show the solution graphically by shading. When you have a two variable quadratic inequality, you show your solution by shading because it's going to be the infinite number of ordered pairs that makes the left less than the right. So remember, your solution, okay, there's an area of the graph that's your solution and an area of your graph that's your non-solution. It is separated by your boundary. Your boundary is when the left equals the right. So the first thing I see is I don't have y by itself. So in order to get the boundary, we're going to want y by itself. Okay? So we take away 2 from both sides. That's going to give us negative y is less than x squared plus 4x minus 3. And then we divide by negative 1 to get y by itself, meaning a coefficient of 1 on y. Because we just divided by a negative, we now need to flip the symbol. So we have y is greater than negative x squared minus 4x plus 3. So our boundary is going to be when the left equals the right. Okay? And then one of the areas is when it's less, and one of the areas is when it's greater. And then your boundary is when the left equals the right. Those are your boundary shape are all of the ordered pairs that if you plug them in, make the equation true, meaning equation equals. Okay? So the first thing we need to do is graph the boundary. So look at the form you're in. You're in standard form. So how would you graph a quadratic in standard form? Okay? You'd get the axis of symmetry first, so that's going to be negative b over 2a. So that's going to be negative negative 4 over 2 times negative 1. That's 4 over negative 2. That's negative 2. So the axis of symmetry is negative 2. So the vertex is going to be negative 2, comma, and so to figure out what the output is, we plug in negative 2. So negative negative 2 squared minus 4 times negative 2 plus 3. Now, people make mistakes here all the time. Make sure you follow your order of operations. You need to square and then make it negative. So negative 2 squared is 4, times it by a negative. This is negative 4 plus 8 plus 3. So that is 4 plus 3, that is 7. So the vertex is negative 2, 7. Now, you're going to want an accurate boundary. You know it's a U shape. So how do you graph an accurate U? You have 5 points in a table. Okay, so I'm going to erase this. I'll put this over here. Okay, I need to make a table of values right now. And my vertex should be in the middle of my table. So negative 2, 7, that's my vertex. I know this is going to be facing down this boundary because look at this, a is negative, right? So I need 2 points on the left to the left of the vertex. So that's going to be negative 3 and negative 4 to plug in, and negative 1 and 0. For right points on the right side of the u. So if I plug in -4, let's see what we get. Okay. Plug in -4 and we get -4 squared minus 4 times -4 plus 3. Make sure you follow order of operations. -4 squared is 16. Now make it negative. This is -16 plus 16 plus 3. That's positive 3. Now 0 and -4 are equidistant from the axis of symmetry. That means 0 must have an output that's the same as -4. And hopefully we did this right because I'm just copying it. If you want to check, just plug 0 in. If they're not the same, that means something is wrong. Either your axis of symmetry is wrong, you plug -4 in wrong, or you plug 0 in wrong. Now we plug in -3, so -3 squared minus 4 times -3 plus 3. -3 squared is 9. 9 times a negative is -9. That's plus 12 plus 3. That's -9 plus 12 is 3. 3 plus 3, that's 6. -3 and -1 are equidistant. They have the same outputs. So 0, 3, -1, 6, -3, 6, -4, 3. So now when you make your boundary, you have to decide, should this boundary be dashed or should it be solid? Oops. Okay, so let's look. In the statement, okay, you can look at this statement or this statement. Is this symbol, okay, is the left allowed to equal the right? No, it can only be greater than, not greater than or equal to. So the boundary is not part of the solution. Remember, your boundary will either be dashed or it will be solid. A dashed boundary implies that that boundary is not part of your solution. A solid boundary implies that the boundary is part of your solution. And the boundary is when the left equals the right. So if the left must be greater than the right and not greater than or equal to, then the boundary is not part of your solution. So your u is a dashed u. Okay? Now, the only way to figure out our plane just got separated into two parts. Okay? We have everywhere inside of this u an infinite area, and we have the infinite area everywhere outside. Only one of those regions makes this statement true. The other region will always make it false. So in order to do that, you have to have a test point to determine this, okay? So we're going to test a point that we know 100% is not on the boundary. I am 100% certain that 0, 0 is not on the boundary because what is the point that's on the boundary? 0, 3. Okay? So you can either plug it into the original or the one that you rewrote. Remember, these are the same value, right? So it does not matter. Just be careful. Make sure you pick one of them and you write it down the correct way. So 0 is greater than negative times 0 squared minus 4 times 0 plus 3. Is 0 greater than 3? That is a false statement. 0 is not greater than 3. 0, 3 is inside of the u. That means everywhere inside is false, which means everywhere outside is true, which means that is your solution. Everywhere outside of the u, if you plug any point in there, it will always make this true. Okay, so that's the only way to represent your answer is by shading the entire infinite region. Okay, so this is what you have to do when you solve a two-variable quadratic inequality. It's just like two-variable linear and two-variable absolute value inequality, except the boundary now is a u. When it was linear, it was a line. When it was absolute value, it was a v. Now it's a u. So that's it for two-variable quadratic inequalities. So now we're going to talk about one-variable quadratic inequalities. So an example would be to solve, and we'll say x squared plus 2x minus 20, whoops, minus, hey, guys, let me rewrite that. X squared plus 2x minus 24 is greater than 0. So notice, you don't have two variables, okay? You're not trying to find the ordered pairs x comma y. that satisfy the statement. What you're trying to find now is, what are the values of x, okay, that make x squared plus 2x minus 24 give you an output that's greater than 0, okay? What are the values of x that are going to make the output of x squared, so when you plug it in, right, when you plug that value in for x, it needs to give you an output that's greater than 0. So what this is essentially saying is, okay, if you were to think about the graph of y equals x squared plus 2x minus 24, you're thinking about name all of the x values in which the y coordinate is greater than 0, okay? So you can think about this by what's called looking at its related graph. So the related graph is going to be, as long as you have it set to be 0 on the other side, this is the related function of this, okay? We're going to look at its graph. So, if I was to sketch this, if I make a quick sketch, what I really care about are, when are the values when this function actually gives me 0, okay? What values does x squared plus 2x minus 24 output 0? Well, I can solve this by factoring, or I can solve this using the quadratic formula. This is going to be x plus 6 and x minus 4. So my values are going to be 4 and negative 6. So if I plug in 4, I'm going to get 0. If I plug in negative 6, I'm going to get 0. But let's talk about something for a second. Okay? So this graph, since a is greater than 0, this graph, whoop, I don't care about the vertex, okay? I'm going to erase this. Okay? I'm going to go like this. And I'm just going to hold on. Negative 6, negative 4. These were our x-intercepts, okay? I'm just going to put some information here, okay? Your x-intercepts are the values when y is 0. So this is the point negative 6, 0, and this is the point 4, 0. So if I was to take negative 6 and plug it in, I would get 0 is greater than 0. If I were to plug in negative 4, I would get 0 is greater than 0. Okay? Now they're obviously not going to be part of the solution, but this is what I'm trying to get at here. If you look at the graph, okay, as long as we have 0 on the other side, all of these coordinate points in here, okay, all of these coordinate points, they have, coordinate point is x comma y. So they have an x and a corresponding y. Every single one of these coordinate points, the y coordinate is going to be negative. When you are below the line y equals 0, all of your outputs are negative. When you are above the line y equals 0, all of your coordinates are positive. So from when x is negative 6 until x is 4, okay, so from when x is 4 until when x is negative 6, all of your outputs are negative. Which means if you plug any number in between negative 6 and 4, your output, you're going to have a negative number. Is a negative number greater than 0? No. Now, this and this is kind of your breaking up point, okay? Everything in between, all of the x's in between have outputs that are negative. Now, this is when the output is 0. This is when the output is 0. Now, everywhere to the left, okay, everywhere to the left of x equals negative 6, okay, negative 7, negative 8, negative 9, negative 10, all of these have outputs that are positive. All of this chunk of the graph, okay, are x's that their corresponding output is positive. So that means all of this, okay? And all of this has positive outputs. So what are these x values that give you positive outputs? This area right here is going to be x is less than -6, and this area right here is x is greater than 4. And it's not an in-between, it's an or. So the answer to this problem, okay, ends up being x is less than -6 or x is greater than 4. You can look at the related graph to figure out this answer. Okay, so let's do a few more of these. So let's move on. Okay, number 2. Let's do x squared plus, let's do 3x minus 21 is less than or equal to 0. Okay, so first we see that it's a one variable because we only have x's, no y. So what this is saying is name all of the x's, just the x's, in which when you input them, you get an output or you get the y coordinate that is less than or equal to 0. So if we look at the graph of x squared plus 3x minus 21, we are going to get a visualization, okay, of all of the inputs and their corresponding outputs. And we need to find all of the x's when the outputs are less than or equal to 0. So what is important is first, when does x squared plus 3x minus 21 equal 0? Because that is going to be the separation, okay? 0 separates your positives from your negatives, okay? So, solve this. Let's see. This is factorable. This would factor to be x plus, oh, let's change this a little bit. We're going to change it so we can actually factor it. Instead of having 3x there, put 4x. 4x. Now, it's factorable. So this will be x plus 7 times x minus 3 equals 0. Remember, if you just want to use a quadratic formula, you can, but I don't want to change that problem here so this works. Okay? So this is -7 and this is 3. So those are the two values in which the output is 0. Okay? So here's -7. 1, 2, 3, 4, 5, 6, 7. Here's 3. Okay, here's 7. -7. Here's 3. Now, is this a U that faces up or faces down? Well, A is positive, so this is a U that faces up. Okay, so now we are looking to figure out, okay, this is 3 and this is -7. Okay? So now what we're trying to figure out is where are the x's when the outputs are less than or equal to 0? So here is where it equals 0, okay? Everywhere you have 3 regions. You have to the left of -7, you have in between -7 and 3, and then you have everywhere greater than 3. So if you look, this region where x is less than -7, okay? These are the coordinates, right? So all of these x's have outputs that are greater than 0. This, remember, up here is where y is greater than 0. This is the line where y equals 0, and all down here is where y is less than 0. So when x is less than -7, your outputs are all positive. So none of this, okay, none of this area is your answer. Now, when you're between -7 and 3, all of these coordinates, x comma y, all of the y's are negative. So right here are all of the x's that are giving you outputs that are negative. So that's from -7 until 3. This area is the area that has outputs that are negative. And then this area here, everywhere to the right of 3, or where x is greater than 3, this doesn't work. All of these inputs for x have outputs that are positive. You could see it graphically, right? these are all positive outputs. So that area doesn't work. So you're stuck in between -7 and 3. Now, are you allowed to be 0? Yes. So that's your answer. This is an and. Okay, this goes back to, these are compound inequality problems. So the answer to this, okay, so first you get when it equals 0. Okay, that's the first thing. Your second is to look at the graph. Now third, answer the problem. So when x is greater than or equal to -7, but less than or equal to 3, that is your answer to this problem. So let's do another. Okay, so for number 3, let's do -x² plus 5x plus 4 is less than 1. Now, you should not start finding the values that make it equal 1, okay? You need to, we're going to reference the graph, and the best point to be at is looking at those x-intercepts, okay? So we care more about not when is it going to be less than 1, okay? We want the right-hand side to be 0. So we should take away 1 on both sides. So that's going to give us -x² plus 5x plus 3 is less than 0. Now, this quadratic, okay, remember the first thing that we're going to do is get when would the x values give me 0, okay? So notice, it's not equal to 0 yet, so that's the first thing we have to do. So -x² plus 5x plus 3, that is the function that we're going to want to look at the graph of, okay? We don't want to look at this graph because we wouldn't be looking at it in terms of 0, okay? This is the one we're going to be working with. So I can't factor this, so I'm going to have to use the quadratic formula. So this is going to be -5 plus or minus the square root of 5 squared minus 4 times -1 times 3 all over 2 times -1. So now I have to simplify this and see what my x-intercepts are. So that's -5 plus or minus the square root of some number over -2. This is going to be 25 plus 12, so that's going to be 37. 37 is not a perfect square, so we want to round this, okay? We want to round so we can understand where these x-intercepts are. So the square root of 37 is 6.083. So -5 plus 6.083 all over -2, and then -5 minus 6.083 all over -2. So let's get our x-intercepts. The first one is -0.542, and the second one is +5.542. So here are our x-intercepts, okay? So graphically, when you're solving a one variable, you don't really care about anything more than the general shape and where the x-intercepts are. So the x-intercepts are at 5.542 and -0.542. And now you need to figure out, okay, does it go, is this a U facing down or is this a U facing up? A is less than 0, so this is a U facing down. I don't care where the vertex is in particular, okay? Now, these are the two x values when the output is 0. You want to know, when is the output going to be less than 0? So you look at your 3 regions. To the left of the first x-intercept, in between the first two in between the intercepts, and to the right of the intercepts. Everywhere to the left, your outputs are negative, which is less than 0. Everywhere in between, your x values give you outputs that are positive, so none of those x's work. And x's that fall to the right give you all outputs that are negative, which is less than 0. So your answer here is x is less than negative 0.542, or x is greater than 5.542. And you don't include these boundaries because you're not allowed to actually be 0. Okay, so now we're going to get into some of the special cases of a one-variable quadratic inequality. So that was 3, so number 4, okay. X squared plus x plus 1 is greater than 0. Okay, so the first is, it's set equal to, not equal to, but 0 is on the one side, so that's good. We see it's a one variable, all right. So first thing we want to know is, when does this equal 0? Okay, so I can't factor this, so I'll use the quadratic formula. -1 plus or minus the square root of 1 squared minus 4 times 1 times 1 all over 2 times 1. That's -1 plus or minus the square root of something all over 2. 1 squared minus 4 times 1 times 1, that's -3. Uh-oh, this is not real. So that means that there are no x values that ever make this 0. That means that this thing has no x-intercepts at all. That means that this graph is one of two things. This graph is either a U that's already above the line y equals 0, that is facing up, or this is a U that's below the line y equals 0, facing down. The vertex is below it. So you look, okay? X squared plus x plus 1. If you were to look at that graph, okay, it has no x-intercepts, okay? Is this going to be a U that faces up or faces down? Well, A is greater than 0, so it is a U that faces up, okay? Now, I'm just making a random picture. It's not going to be perfectly accurate. But understand that it's going to look something, I mean, it could be shifted anywhere up, a little bit more up, left, right, but what I'm trying to get at is this function has no x-intercepts and it's facing up. So it's never going to touch this line y equals 0, and every single piece of the quadratic is above. That means every single x value, if your entire function is above the line y equals 0, that means every single x has an output that's greater than 0. So this is saying, name all of the x's in which the output is greater than 0. Well, since you have no x-intercepts and the entire function is above, that means that every single x value that you can plug in for x will give you an output that is greater than 0. So this is all real numbers. That is the answer to this question. All real numbers. Okay, so let's do another one. Okay, so that was 4. Number 5, let's do x squared plus x plus 7 is less than 1. Okay, so first off, you don't want to have anything but 0 on one side of the statement, so I will take away 1 from both sides. So we want to know, when is x squared plus x plus 6 going to be less than 0? Okay, so this is the function we're going to be working with. We would want to see the related graph of this, but the first thing we want are the values when x squared plus x plus 6 actually equals 0. That way we can figure out where are the x's that are less than 0. So we can use the quadratic formula because we can't factor this, so that's -1 plus or minus the square root of 1 squared minus 4 times 1 times 6 all over 2 times 1. That's going to be -1 plus or minus the square root of something over 2. 1 minus 24, that's going to be -23. Okay, I have a negative number right there under the square root. That means that my solutions are not real. So that translates to no x-intercepts. So what that means is there are no values of x that make this equal 0. So graphically, this is doing one of two things. Either it's a u facing up that's already above the line y equals 0, or it's a u facing down that's already below the line y equals 0. So you look, a is 1, which is greater than 0, so this is another case of my entire quadratic is already above the line y equals 0. So every single x gives you an output that is greater than 0. And this problem says, name the x's that are less than 0. Okay, name the x's that are less than 0. Well, there are no inputs that can ever give you an output that's less than 0. So the answer to this is no real solution. There's no real solution to this. There's no value, okay? There's no real value that can make this 0, okay? Look, when we get our complex number, imaginary number there, we know this has no x-intercepts. So you have to decide, is it a u facing up or is it a u facing down? And then with respect to, am I looking for greater than or less than? So this time it's no real because there are no outputs that are going to be negative, okay? That's what less than 0 means. Your outputs are less than 0. All right, so one more, and then that'll be it for one variable quadratic inequalities. All right, let's do, that was 5, it's number 6. Let's do x squared plus 10x plus 25 is greater than or equal to 0. Actually, let's do is greater than 0. Not greater than or equal to, sorry. Is greater than 0. Okay, so, we see it's a one variable quadratic inequality. 0 is on the other side, that's good. That means we want to know when is x squared plus 10x plus 25 going to equal 0. So try and factor it, it's factorable. If not, go to the quadratic formula. This is x plus 5 times x plus 5. So we get -5 twice. So that means this only has one x-intercept. And the one x-intercept is -5. So what that means is that if you only have one x-intercept, that means that x-intercept is the vertex, okay? And so is this a u facing up? Okay, it's at -5. Is this a u facing up or a u facing down? Well, a is 1, a is greater than 0, so this is a u facing up. So, in this case, this is a special case. We only have one x-intercept. So the regions are to the left of -5, to the right of -5. Everywhere to the left of -5 and to the left of when x equals -5, your outputs are all positive. To the right of -5, all of your outputs are also all positive. But when x is -5, your output is 0. So every real number but -5 has an output that is greater than 0. So the answer, you can say one of two things. You could say all real numbers except -5, or you could say x is less than -5 or x is greater than -5. This means everything but -5, okay? So be careful when you have your special cases are going to be no x-intercepts or one X-intercept. Be careful. Make sure you read carefully what it's asking you. Okay? This is saying, when are your outputs going to be greater than 0? Your outputs will always be greater than 0, except when x is -5, it's going to be 0. So your answer, okay, when you have a one-variable quadratic inequality, notice this, there's no graph that's an answer. This is one dimension. You could put it on a number line if you wanted to, but this is just in terms of x. Okay, one-variable quadratic inequalities are in terms of just x, or whatever the input letter is. You're not showing it graphically. You don't do two variables, okay? You want to know just what it is in terms of x. If you wanted to plot your answer on a number line, you could, but you don't have to. You can just give it in terms of what the solution is for x. So that's it for quadratic inequalities.